Welcome to this fascinating exploration of the slip flow illusion. Today we're going to uncover one of the most intriguing paradoxes in fluid mechanics: how liquids can appear to slip along surfaces where they absolutely should stick. To understand this paradox, we first need to understand one of the most fundamental principles in fluid mechanics: the no-slip boundary condition. In classical fluid mechanics, when a fluid flows along a solid surface, the fluid molecules that are directly in contact with that surface have exactly the same velocity as the surface is. Here we see a classical velocity profile. At the wall, the velocity is zero. As we move away from the wall, the velocity increases. This creates what we call a velocity gradient. This means that if the wall is stationary, the fluid velocity right at the wall must be exactly zero. No exceptions. This is the no-slip condition. Why does this happen? The fluid molecules are held in place by strong adhesion forces between the fluid and the solid surface. These intermolecular forces essentially lock the fluid layer to the wall. But here's where things get interesting. In hydrophobic microchannels, something remarkable happens that seems to violate this sacred principle. Experimentalists notice that when water flows through very small hydrophobic channels that repel water, the flow rate is significantly higher than what classical theory predicts. On a hydrophobic surface, the fluid appears to have a non-zero velocity right at the wall. It's as if the fluid is slipping or gliding along the surface instead of sticking to it. The liquid appears to glide where it should stick. This is our paradox. This is the slip flow illusion. So here's a critical question. Is the no-slip boundary condition actually being violated? Is one of the most fundamental principles of fluid mechanics wrong? To quantify this apparent slip, we introduce a parameter called the slip length. The velocity at the wall equals a constant b times the velocity gradient at the wall. This constant b is called the slip length. The slip length b represents the distance below the surface, where the velocity would extrapolate to zero if we extended the velocity profile into the solid. Here you can see the slip length graphically. If we extrapolate the velocity profile downward into the solid, the slip length is how far below the surface we would need to go to reach zero velocity. For ordinary wetting surfaces, the slip length is essentially zero, or maybe a few nanometers. Completely negligible. But for hydrophobic surfaces, especially in microchannels, the slip length can be anywhere from 10 to even 1,000 nanometers. This becomes significant at small scales. Let's look at how slip flow affects the classic Hagen-Poiseuille equation for flow through a pipe. The classical Hagen-Poiseuille equation states that the volumetric flow rate Q equals pi times the radius to the fourth power times the pressure difference divided by 8 times the viscosity times the length. This equation assumes perfect no slip at the walls, but what happens when we have slip? With slip, the flow rate is enhanced by a factor of 1 plus 4 times the slip length divided by the radius. Notice something crucial here. The smaller the channel radius r, the more significant the slip effect becomes. This is why slip flow is especially important in microfluidics. Let me give you a concrete numerical example to show you how significant this effect can be. Suppose we have a microchannel with a radius of 1 micrometer, which equals 1,000 nanometers. On a hydrophobic coating, the slip length might be 100 nanometers. 4 times b divided by r equals 4 times 100 divided by 1,000, which gives us 0.4. This means the flow rate with slip is 1.4 times the no-slip flow rate. That's a 40% increase in flow rate. A 40% increase in flow rate just from this slip effect. This is huge in microfluidic applications. Now let's dig into the physics. What's actually happening at the molecular level that creates this slip effect? Here's the key insight. It's not actually true slip at the molecular level. The no-slip condition is still valid. What happens is that hydrophobic surfaces tend to trap tiny nanobubbles of gas, or they create what we call depletion layers, where the water density is lower. These nanobubbles create an effective gas-liquid interface. The water molecules don't actually stick to the solid. They're flowing over these tiny gas pockets. The fluid still satisfies the no-slip condition at the true liquid-solid interface. But because there are these gas pockets, there is less solid surface for the liquid to stick to. Here's an analogy. Imagine you're skating on ice versus walking on concrete. On ice, there's actually a thin layer of liquid water between your skate and the ice. You're not really sliding on solid ice. You're gliding on a liquid layer. Same principle here. Now let's look at a theoretical formula that predicts the slip length based on surface properties. The slip length B equals 2/3 times lambda times the quantity 2 minus F over F. Here lambda is the mean free path of the fluid molecules, and F is the fraction of the surface that's actually solid. When F equals 1, meaning the surface is completely solid and wetting, the slip length becomes 0. No slip occurs. When F is less than 1, meaning there are gas pockets or the surface is only partially wetting, we get a positive slip length. For example, if 80% of the surface is solid, F equals 0.8, then B equals 2/3 lambda times 0.25. For water at room temperature, the mean free path lambda is approximately 0.3 nanometers. This gives us a slip length of about 0.05 nanometers for F equals 0.8. This is quite small, which tells us we need very low F values to get significant slip. So here's an important question. How do we actually achieve large slip lengths in practical applications? The answer is engineered superhydrophobic surfaces. These are surfaces with micro or nanoscale textures that trap air. These surfaces have tiny pillars or ridges that trap air pockets between them. The liquid sits on top of these pillars, creating what's called the Cassie Baxter state. Now F can be much less than 1. Now let's talk about another fascinating aspect. How does slip depend on the shear rate? The shear rate gamma dot is defined as the velocity gradient dV by dy. At low shear rates, the slip length remains essentially constant. It's a property of the surface. But at very high shear rates, the slip length can actually increase. This happens because the high shear forces can deform or even rupture the interfacial layer. Some models propose that the slip length equals a baseline value B0 plus a coefficient alpha times the shear rate. This creates an interesting nonlinear relationship between flow rate and pressure drop, which deviates from the classical linear relationship. Let's talk about why this slip flow phenomenon matters in real-world applications. In microfluidic devices, slip flow can reduce the required pumping power by anywhere from 40 to 100%. This is huge for portable diagnostic devices. In drug delivery, understanding slip can help us design better systems for transporting medication through narrow capillaries and tissue channels. In nanofluidics, when the channel dimensions approach the slip length, slip effects completely dominate the flow behavior. In industrial applications, superhydrophobic coatings can reduce drag on ships and pipelines, potentially saving enormous amounts of energy. Let's look at this from an energy perspective, which gives us another way to understand slip flow. The rate of energy dissipation per unit volume equals the viscosity times the integral of the velocity gradient squared over the volume. With no slip, we have the maximum possible velocity gradient right at the wall, which means maximum energy dissipation. With slip, the velocity gradient at the wall is reduced. This directly reduces the energy dissipation, which is why we get enhanced flow rates. The ratio of energy dissipation with slip to without slip equals 1 divided by 1 plus 4 B over R. The same factor we saw earlier. How do scientists actually measure these tiny slip lengths experimentally? It's quite challenging. One method is to measure the flow rate through a microchannel and compare it to the theoretical no-slip prediction. The deviation tells you the slip length. Another method uses atomic force microscopy. You measure the force required to squeeze fluid between an AFM tip and a surface. Slip affects the drainage rate. A third method uses particle tracking velocimetry. You track tiny tracer particles near the surface and directly measure their velocity profile. The challenge is that slip lengths are typically only 10 to 100 nanometers. You need extremely precise measurements to detect such small effects. Now I want to address an important theoretical controversy that has surrounded slip flow. Here's the controversial question. Can true molecular slip occur even on perfectly smooth surfaces, purely from weak fluid-solid interactions? Some molecular dynamics simulations suggest yes. If the fluid-solid interaction is weak enough, molecules might not fully equilibrate with the wall. However, most experiments show that significant slip requires some form of surface heterogeneity, like nanobubbles or roughness. The current consensus is that intrinsic molecular slip does exist, but it's usually negligibly small, just a few angstroms. practical slip requires surface features. There's a beautiful connection between slip flow and the famous lotus leaf effect. Lotus leaves are superhydrophobic because of their micro and nanoscale hierarchical structure. Water droplets beat up and roll off, picking up dirt as they go. The same principle is at work. The textured surface traps air, creating effective slip between the water and the leaf. The droplets essentially roll on air. This has inspired engineers to create biomimetic surfaces that mimic the lotus leaf structure for self-cleaning and drag reduction applications. Before we conclude, let me mention that slip flow appears in several other interesting contexts beyond liquids. In gas flow at low pressures, when the mean free path becomes comparable to the channel size, we get slip flow due to rarefaction effects. This is characterized by the Knudsen number. In polymer melts, you can get wall slip when the polymer chains near the wall disentangle from the bulk. This is crucial in polymer processing. In blood flow through capillaries, red blood cells tend to migrate away from the walls, creating a cell-depleted layer. This plasma skimming creates an apparent slip effect. Let me summarize the key concepts we've covered about the slip flow illusion. The fundamental no-slip boundary condition is not actually violated at the molecular level. It remains valid at the true fluid-solid interface. Apparent slip arises primarily from nanobubbles, gas pockets, and surface heterogeneity that create effective fluid-gas interfaces. The slip length B quantifies the magnitude of the slip effect. For hydrophobic surfaces, it's typically 10 to 1,000 nanometers. The flow rate enhancement scales as 1 plus 4 times the slip length over the channel radius. This becomes significant in microchannels. Applications range from microfluidic devices and lab-on-chip systems to drag reduction coatings and advanced materials. Understanding slip flow requires considering phenomena at multiple length scales, from molecular interactions to macroscopic flow patterns. The slip flow illusion beautifully illustrates how a seemingly simple principle like no slip can have subtle and surprising exceptions when we look at the right length scales and surface properties. It reminds us that in science, apparent paradoxes often reveal deeper truths about how nature works at different scales. This field continues to evolve rapidly as new nanofabrication techniques allow us to engineer surfaces with unprecedented control over slip properties.